In extreme cases, the tidal forces can distort the shape of celestial bodies, up to the point of breaking them. Some planetary rings, such as Saturn's, seen here by NASA's Cassini probe, may be the result of the destruction of a satellite under the effect of tidal forces. We will see here that there is a limit in the distance between the two bodies before one of them breaks under the effect of the tidal forces from the other. This distance is known as the Roche limit, from the French astronomer Edward Roche, who first performed the calculation in the 19th century. Let us compute the Roche limit, the distance at which a satellite is destroyed under the effect of the tidal forces exerted by a planet. Let us consider a planet of a given radius r. Here is Jupiter as an example. We assume it has a constant density, m. We also consider a satellite, Io for example, or any other satellite, which has a given density, m, and a given radius, r. The two bodies are at a distance, d, from each other. We saw in the last chapter that we have tidal forces exerted on the points A and B here. These are differential forces due to the gradient of the gravitational field of Jupiter through the satellite, namely Io in this example. The tidal forces are equal with opposed signs. We have a force here on B and another one here on A. Both forces are stretching the satellite. We previously found that the tidal force, when neglecting the rotation of the satellite around Jupiter, exerted either on B or on A, has the same value, is equal to 2gm divided by d, with d the distance between the two bodies, times the radius of the smallest object. This is the expression of the tidal forces when neglecting the rotation of the satellite around the planet. What happens when we do not neglect the orbital motion of the satellite anymore? The angular velocity is given by 2 divided by p, where the orbital period p is given by Kepler's laws. We have a centripetal acceleration at the 3 points here, at the center, and at the edges of the satellite. This centripetal acceleration is A equals r, where r is the distance between the center of Jupiter and each point we are considering. We had the points A and B there, as well as the center C of the satellite. Let us consider the different forces. There is first the centripetal acceleration. On the closest point to Jupiter, A, it is smaller than on the other points, such as C here, or B there. The acceleration on A is d minus r. At the center, we have an acceleration d. Since the center is at the distance d from the center of Jupiter, and on B, the centripetal acceleration is d plus r. We have thus a centripetal acceleration to the center of Jupiter. At each point on the surface of the satellite is felt a pseudo-force, in particular at the points A, B, and C, the center of the satellite. So we have, like previously, A, B, and C. The pseudo-force is in the opposite direction, with a norm equal to the norm of the centripetal force. We have thus a small vector here on A, a bigger vector here on C, and an even bigger one on B, such that the norm of the different accelerations are the ones we wrote previously. We now want to compute the differential acceleration at the points A and B relative to the acceleration at point C. To this purpose, we subtract at A, B, and C the centripetal acceleration, or the pseudo-forces felt at C. We add a vector with the same norm as this one at C, but with opposed direction. We have then a first arrow at C here and another one at B there, such that they have the same norm. and at least one at A, they're with again the same norm. We add the two vectors at each point, and we get the resulting force. Here at B, we have a force roughly like that. At the center, we have obviously 0. And at A, the resulting force is in this direction. We are now interested in computing the norm of these two green arrows. Let us first write the norm of the green arrow at point B. The acceleration at point B is d plus r minus d, which is simply the difference between the white and the red arrows. So finally, equals r. The third Kepler law tells us that d divided by p equals gm, where m is the mass of the most massive body, over 4 with equal 2 divided by p, p being the orbital period. From there we deduce that gm divided by d that we inject here in order to get the acceleration at point B. It is equal to gm divided by d times r. As we've seen before, the tidal acceleration at point B, caused by the gradient of the gravitational force through the satellite, equals 2gm divided by d times r. We thus have an effect on differential rotation. The differential acceleration caused by the rotation of the satellite around the planet, which is equal to half the tidal force, and as such is by no means insignificant. Now let us summarize what we computed. We still have our 2 points, A and B. We will look in greater details what happens at point B. We have our satellite with a radius r, and we have several forces. We have first the tidal force that we computed in the previous video, the differential acceleration, which is half of this force there, and in the other direction we have the g of the satellite. So here is the tidal acceleration, which is equal to 2gm divided by d times r. We have the centripetal acceleration we just computed, which is equal to gm divided by d times r. The satellite is torn apart. If the norm of the sum of am plus the tidal acceleration so the sum of the two forces is greater than the norm of the gravitational field, which holds the satellite together. If the sum of these two accelerations is greater than g, then the satellite is destroyed. Let us write it as equations. 3gm divided by d times r, gm, where m is the mass of the satellite, over r, its radius. This term is the gravitational field at the surface of the satellite. To simplify, we will assume that m equals 4 divided by 3, r times m, rho m being the satellite density. With the same assumption, the mass of the planet, Jupiter here, is m equals 4 divided by 3, r times m. We consider to be constant. If we plug m and m in this equation here, we will find a critical distance we are interested in. d Roche equals 1.4 times the ratio of the densities of the two bodies to the power 1 divided by 3 times the radius of the larger body. Jupiter in this case. This is an approximation that does not take into account the internal cohesive forces. If we make an exact calculation, we would find here a factor 2.5. This distance, d Roche, is the one we have to inject in this equation here to have equality. If the distance is smaller, the satellite is torn apart by the combined effort of tidal forces and centripetal acceleration caused by the planet. Let us come back to the planet Saturn. The rings you see here are the result of the breakup of a body that crossed the Roche limit and broke under the effect of the tidal forces from Saturn. But all the rings don't have the same origin. The external ring, the E ring of Saturn, slightly blurred on this picture, taken by the Cassini space probe, is actually created by the extreme volcanic activity of a satellite of Saturn, Enceladus. The plumes that you see going out of the satellite are composed of water vapor, heated partly by the friction of matter in the internal mantle of the satellite under the effect of tidal forces from Saturn. Part of the water vapor is ejected to the orbit of the satellite with some dust. This process creates a wide ring materializing the orbit of Enceladus around Saturn. In the solar system, the bodies most affected by the Roche limit are probably the comets. They travel at high speed through the whole solar system, and therefore get often quite close to strong gravitational fields, such as Jupiter's or the Sun's. In both cases, the comets can be destroyed if they cross the Roche limit. This is what happened to the comet Shoemaker-Levy 9, getting too close to Jupiter in May 1994. The comet broke up into 21 pieces, clearly visible on this picture taken by the Hubble Space Telescope, where we see debris spreading over a distance of more or less 1 million kilometers. 3 months later, these debris came back to Jupiter and eventually crashed on the surface. On 16 July 1994, several impacts were visible on the planet's surface for several days. Some impact marks even reached the size of the Earth.